Okay, hi. So this is the famous orbitals of S, P, and D. And here we have the, as you see, is the S orbital on the three axes, X, Y, Z. So the X, Y, Z are the three dimension axis, which we can see the direction of the motion or move of any species. So the S orbital is look like this, spherical. It's like a ball, spherical, and this is the real space of the S orbital. So the S orbital is a space where can occupy electron or two electrons, or even it exists without electrons. So the the S orbital shape is called spherical. So it's in the center of the XYZ and it's moving. P orbitals are three suborbitals. The first one, as we said, the 0 1 is the PY. You remember the ML? ML is 0 and ML minus 1, ML plus 1. So the ML 0 is a PY to the left, it's a PX and PZ. So it's always like when we name um, an orbital, the orbital, where it is, what's the shape of the orbital, how can it moves clockwise, how many electrons inside. So as we know that the orbital is a space where can occupy an electron. So the electron cannot leave this space and unless it has energy to escape from this space or from this orbital or suborbital. So here we have the XYZ. If, of course, the p orbitals they are in two loops, we call them. There are 3p suborbital made up of two loops called dumbbell shaped. These dumbbell shaped aligned along perpendicular axis. Aligned perpendicular axis. Perpendicular. It's on the axis. Located on each side of the plane that runs across the nucleus. They oriented differently. So the orient, the move, the motion of the orbital itself. So that we have a motion for electrons and we have a motion of orbital itself. So two loops, each loop can contain one electron or more. So now these are the movement. So px, it means the electron in or the orbital exactly sitting on the x-axis or aligned perpendicularly on the x-axis. The py is perpendicular to the y-axis. Two loops. And the z-axis here, as you see, is perpendicular. The orbital is aligning perpendicularly on the z-axis. It means the orbital is here. It cannot go a different direction. Now, if we come to the d orbitals, there are 5 d suborbitals. 5d, 1, 2, 3, 4, 5. Four of them are with 4 loops. Only dz square have 2 loops, and in the middle there are like a cloud in the middle. So the alignment of these 4 loops, again, if we call the first one is dxz, it means that 4 loops aligned on the x and z. So see, 2 loops on the x and 2 loops on the z, should be at the z. dxy, they are in between. The 4 loops in between the x and y, in between, in the middle. dyz, the dyz, it means it's between the y and z, dyz. And we have dx square y square. It's not minus, but we pronounce it as dx square y square. So they are perpendicularly aligned on the 2 of them on the x, 2 of them on the y. So we call them dx square. It means they are on the x square. And here I didn't say that the dxz, they are between the x and z. We come to the dz square. There are 4 loops, but 2 of them condensed in the middle. So we call they are all on the z axis. So they are dz square. Now here we are. We can see the loops on the plane or in the plane. The dyz between the y and z, the dxz and the dxy between the x and y. This is the x, this is the y. So the loops are between them. dx square y square, the loops exactly, this is the plane. So they are exactly on the x or the ax of y and the ax of x. So dx square y square. The dz square, 4 loops are on the z square. Now we come to the periodic table. We have to know exactly how are the periodic table being built or made or organized or arranged. So in the 1869 to 1870, Dmitry Mendeleev and Luther Meyer stated properties of elements can be represented as periodic functions of their atomic weight, of their atomic weights. Okay, so the property of elements can be represented by the function of their atomic weights. But the modern periodic table depends on blocks of 2, 6, 10, and 14 elements, which result from the filling the SPDF orbitals respectively. IUPAC, International Union of Pure and Applied Chemistry, has produced way of naming blocks and groups of elements in the periodic table. So there are group 1, they call them alkali metals, where they have 1 valence electrons at the last orbital, and they possess low melting points. Group 2 alkaline earth metals, they have 2 valence electrons at the final orbital, and they are high in melting points. Group 15 pnictogens refers to choking property of nitrogen gas. So they call them pnictogens. So they are nitrogens and oxygens. And group 16, chalcogens, the ore forming elements. Ore forming elements, that's the group 16. Whereas group 17 are the halogens and group 18 noble gases. So the main group elements are 1 and 2, which they end up with s orbitals. 13 to 18, they are ending with p orbitals. The transition d block elements in group 3 to 11. Okay, so these are the general talk about periodic table. Let's see how the elements are organized or arranged. As you see here, periodic table in colors. So I put the color to separate the or put the groups of elements which they possess like general chemical and physical properties. So when we come to hydrogen, and hydrogen is a gas, so hydrogen and these elements here, so 1a and 4a, okay, let's say the hydrogen is a gas, and here are the gases as well. These two groups here, okay, the periodic table are made of rows and periods. So rows or columns and periods. So the column, let's say the rows are starting with hydrogen, lithium, sodium. Let's say from lithium to francium, and from beryllium to radon to radium, they are metals. All these are metals, and we know sodium, magnesium, calcium, potassium, strontium, rubidium, cesium, barium, francium, and radium. They are all in as metals. Whereas we come here, these dark green group, carbon, nitrogen, oxygen, fluorine, they are not metals at all. And in between here, boron, silicon, the rest, they are in blue. These are metalloid, so they possess kind of a property of metals and non-metals. Okay, so we move to the middle here. From scandium to zinc, from atomic number 21 till 30, and this period as well, fourth period, fifth period, all of these are transition metals. So these groups here, and the lower one, which are the lanthanides and actinides. So they've been made or named by lanthanum element and actinium, lanthanium and actinium elements for these two groups. So here what we have are the groups of transition metals, and they are mostly used in the coordination chemistry or the coordinated bonds. You can find periodic table like many information in them, and they put together in specific colors or more information being written about each element. So most like what we see numbers here are the atomic numbers. So usually they arranged, or not like Mendeleev table, as we said here, Dmitry Mendeleev, they arrange them with with their atomic weights or masses, but this one is by atomic number of electrons. Now we come to the naming and symbols. If we, to simplify writing equations and using these atoms in chemical bonding or structure, we have to put them in codes. So every word or of element is being given a code name or a code letter. So we can find only one letter as big. We can find other element big and small letter. So just to differentiate between hydrogen and helium, if we write H and H, they are similar. So sometimes we only depend on the first letter, and sometimes we depend on the first and second letter. Okay, these are most of the elements, they come like this. But some elements been named or coded with the Latin name. Like if we see here, sodium is Na, it's not So. So Na came from natrium. So sodium, the Latin name of sodium is natrium. Magnesium is okay, aluminum is okay, silicon, phosphorus, sulfur, chlorine, argon. But if we come to silver, silver is being written as argentum, Ag. So the Latin name of silver is Ag. The Latin name of mercury, Hg, mercury, is hydrogium. So the mercury is hydrogium, so they choose Hg from the Latin name. The lead, Pb. So we could expect lead is giving Le, but it's being given Pb. Pb came from plumbum. So the Latin name of lead is plumbum. And the last one is the gold, Au. It's given the name Au code, which is aurum. Aurum is the gold. So as we see, sometimes we depend on the Latin name to put the symbol of the element, or we can depend on the English name. So determining the ground state electronic configuration. How can we determine the ground state electronic configuration? Here we have many rules. The first one is Aufbau building up principles. So it means how can we do the electron configuration. So the Aufbau principle talked about orbitals are filled in order of energy. The lowest first energy orbitals being filled, and then the second one. The Hund rule. Hund rule talk about electrons singly occupying orbital, then coupled. The Hund rule. Pauli exclusion. No two electrons in the same atom have the same set of quantum numbers. Each orbital can take a maximum of 2 electrons with different spin. Okay, so that's what we talk about, the spin, up and down. You put it, the arrow should be standing or opposite. It means clockwise, anti-clockwise. So these are the 3 principles when we build up the electronic configuration. This drawing here, how you start filling the orbitals, because they are not, they can reach to a point then there will be overlap between the orbitals or suborbitals. So when we put this, you can put 1s, 2s, 2s, 3s, 4s, 5s, 6, 7, 8, 9s. Then you could put beside it, you have to memorize this drawing. You put 2p, 3p, 4, 5, 6, 7, 8. Then the third, the main shell 3 contain 3D. So you put 3D and then 4D, 5D, 6D, 7D. The 4F comes next, 4F, 5F, 6F. So when you start filling the orbitals from the lower energy level and jump to the next one, so you have to follow this arrangement. So we start with 1s, fill it with 2 electrons, 1s2, then 2s2, then come back 2p6, 3s2, 3p6, 4s2, 3d10, 4p, 5s, or 4p6, 5s2, 4d10, 5p6, 6s2, 4f, 14, 5d10, 6p6, 7s2, and so on. So you have to see here, no problem with 1s2, 2s2, 2p6, 3s2, 3p6. You don't, it's not allowed to put a 3d after 3p because there is overlap. 4s lower energy level than 3d. It's been found by magnetic machines and other devices and analytical devices. They found the 4s is less energy level than the 3d. So the 4s comes first, 4s2, 3d10, then 4p6, and s, 5s, is lower energy than 4d. And you can follow the other arrangements of the orbitals. So if we take example of write the electron configuration for magnesium 12, argon 18, or the rest, or you can write the element name. What is the element name of the O, K, Ba, Cl, B, P, Be? So either we give you the symbol or you give us the symbol. So if we come to B5, boron, 5 electrons. Electron configuration is 1s2, 2s2, 2p1. You see, 2, 2, and 1, 5. So the last electron, which determine the property of the element, is in P. This electron here is very important. The last one, because these electrons are shielded. They call them shielded. And the shield, it means they don't show off themselves. They can't. So the one at the higher energy level is the only electron can determine the property of, or most of the property of the element. So the 4 quantum number for the 2p1 is what? So 2p1, 2 is the main, is a principal quantum number, p is the orbital quantum number, 1 is what? Is the spin, we can call it, 1 electron in the spin. So we can give the n equals 2. L is a p. So when L is a p, so as we said, S take the 0, P takes 1. So L will be 1. ML is where is the electron sitting? ML. So the electron sitting not in the middle, not to the right, but to the left. So it's sitting in the +1. And the MS is the spin quantum number. Standing clockwise, it's a plus half. So question, write the electron configuration for N7, chlorine, phosphorus, nickel, krypton. So you can do that. And write the 4 quantum number for electron, the last subshell. Be careful how you write the electron for the last, because the 4 quantum numbers belong to the last electron in the final higher energy level shell. 4 quantum numbers, if you've been given 4 quantum, N is 4, L is 0, ML 0, MS minus half. So identify the atomic number and element name. So now if we answer this, the last subshell is N is 4, so you say 4. L, when L is 0, it means the orbital S. So we write is 4s. Okay, the ML is the electron sitting in S, so it has the orbital magnetic momentum, angular momentum, orbital magnetic momentum is a 0, so it's sitting in the S. The S takes only 0. MS is minus half, it means the electron is at the lower position or the anti-clockwise. It means this orbital is filled. The S orbital is filled with this one, but the last one is lower or anti-clockwise electron spin. So because minus half, so we have to add another electron to this one. So it will be 4s2. If we come to the 4s2, we have to bring the electron configuration from here, and we have to reach to 4s2. So we have to start with 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. So these all filled with electrons, okay, to solve this problem. And in this case, 1s2, 2s2. So now we do the total number of electrons, 2, 2, 6, 2, 6, 2, and you can put the D0, no problem. So we have here, it is the calcium. So I can get rid of this, because it's, we said it's 4s comes before 3d. So the 3d, I have to write it down, but the last orbital is occupied by 1 electron, is the 4s2. So now we make the total 2 and 2 and 6, 10, 2 and 6 and 2, 10, so they are 20. 20, we come back to the periodic table, which should be given, and we look for the 20 is a calcium. Okay.